Hello again, I am Doğan Canbor and I am going to explain the near field scanning optical microscopy, or in short NSOM, under the assignment of task 6 of EE495, Fundamentals of Photonics. I have my notes over here, so let's go through it together. Okay, when we are focusing images, we have a limitation, which means that we cannot size images as much as we want. This limitation results from diffraction of the light waves, and it is called the diffraction limit of the light. As a result, after a determined point, we would only see blur instead of our object, and this limitation was discovered by Ernst Abbe, which is this guy over here, in 1873, who claimed that when we are using a wave with a wavelength of lambda to resolve objects separated by delta x from each other, we have a limitation such that delta x should be greater than lambda over 2 times numerical aperture, which is approximately equal to 200 nanometer for visible light range. This means that if we set our delta x, if we set our objects closer than 200 nanometers to each other, we would only see one blurry object instead of our object 1 and object 2. This limitation makes resolving objects smaller than 200 nanometers problematic. To overcome this problem, Edward Sinch, which is this guy over here, suggested in 1928 to use a screen with an aperture smaller than the wavelength of incident light, and 2 regions will be created as a result of this. Here we have our aperture on the screen. This is our screen, okay, this is our screen. This is our aperture, and as can be seen, our aperture is smaller than the lambda, and we have our incident light coming from upside, okay, and near field region and far field region will be created as a result of this aperture on our screen. On near field region, there is no diffraction limit, whereas the diffraction is dominant in the far field region. Near field region can be said that it is a confined evanescent wave, hence as you get further from the screen, the near field decays exponentially, as can be seen here. And if we place our sample within the near field, we would overcome the diffraction limit and image or resolve the things smaller than 200 nanometers with the visible light. Now let's talk about the general instrumentation of this concept. As can be seen, we have a laser as our light source, and we have a fiber optic probe with a small aperture on the top of it. Here's our aperture, and as I have explained earlier, this should be the aperture should be smaller than the lambda, which is the wavelength of our incident wave. Okay, we have a fiber optic probe with a small aperture, and we have our tuning fork, which tells us the frequency as our probe tips moves further or closer to our sample. And this is our sample, and as can be seen, it is very small, actually smaller than 200 nanometers maybe. Okay, so our laser comes from the fiber optic probe. It goes through our sample, and as can be seen, we created a near field region and far field region here. And as light is coming to our lens is focusing these lasers, these lights, to an avalanche photodiode. And this avalanche photodiode turns our light into an electric signal and sends it to our computer to process the signal and give us data. By this instrumentation, we are able to resolve the objects smaller than 200 nanometers or multiple objects which are standing in a distance closer than 200 nanometer range. This covers the topic of the near field scanning optical microscopy, and thank you for listening. I wish you have a great day. Goodbye.